we want you to calculate the one more state, size state, last time some of you did real or complicated. It's not that complicated. So what you need to do is essentially like this. So this is my wave function. I will give you the wave function, let's say ground state wave function. So this is my ground state wave function like that, phi. And you have some bunch of a coefficient in front. That's the normalization coefficient. And the e to the whatever, then we call it the lambda, because they have a lot of coefficients in front like that. So this is the ground state wave function. Now, if we want to find excited wave function, watch carefully how we do that. Watch carefully. So we use the A dagger, A plus like this. Now, there's nothing else need to be done except you know A dagger has some coefficients, and first term is x, second term has some coefficients in front, and second term the p head like this, right? So this is the A dagger, probably is a minus sign there, probably minus sign, I think it must be minus sign, like that. So this is the wave function. You must write this down now. When you got this, this only about 4 minutes calculation, maximum 5 minutes calculation. How do you do that? Did you see our first term is x? Did you see our first term x? So then I will have ax mod e to the negative like this. That's my first term. Second term, you remember have some coefficients. Watch carefully. The second term is extremely simple. All you need to do is this. You remember this operator is partial x. Then this the function look like that. So in other words, all we need is such simple. This is already in the good position. You don't need to do anything with it. Because already good position, there is nothing need to be done. Except watch carefully. You need to take derivative with this guy. You take derivative with this guy and then arrange in such a way, make them look nicer. That's end of it. So you take derivative, that's it. Less than 4 minutes, I will promise you. Less than 4 minutes. You got it, less than 4 minutes, because this is constant, and you take a derivative, and then eventually you get this result. So the first term like this, and you've been able to combine these two terms. If you want to do the second exercise, this is the first exercise. If you got the second exercise, you do twice like this. There's nothing else that you need to do. Make sense? Make sense? So that's how we do the calculation. You know what's the hardest one after the beginning? Hardest one we need to solve differential equation. But later on, just take derivative, just keep on going. That's how you do it. So that's one that I want you to remember how do we do this. And then we already mentioned, what about to representing the harmonic oscillator? Cody, are you on the concept 2 page?
Yeah, sure.
Should be in review test 2, like that. Yeah, good, right. And then now number 5, difference between Schrödinger and Heisenberg pictures, and then you need to specify what the difference. And we talk about which picture can represent a state evolution. Tell me, which state can represent state evolution? Heisenberg picture or Schrödinger picture? State evolution.
Schrödinger.
Exactly. It must be Schrödinger. Schrödinger, the Heisenberg has no states, and so this is just operators. Good job. Now, how to use the Heisenberg picture to find the solution in the harmonic oscillator? And this is already showed you last time. Essentially, you can use it, use the harmonic oscillator to do the calculation. When you do that, you got to remember a few things like this. For instance, you got to remember A dagger equals. So this is the operator A harmonic oscillator like this. So you will be asked to calculate something like this. So I give you an expression, and I want you to calculate t whatever the time that will be. This is the operator of evolution, and then Schrödinger is the state of revolution. So that's what you need to. Could you guys write this down, please? That's also very important for that one. And so, for instance, the bottom ones here, I want you to calculate dx over dt. So we look at the equation, I'll look at the Hamiltonian, is h equals p sub x squared over 2n, and then remaining all these terms like this, and then find the dx over dt. And that is exactly what I'm talking. For instance, if I want to calculate dx over dt, now this is just operator, annihilation operator, but if I want you to calculate the dx over dt, you do the exact same thing. Here's x operator and h like this. So all you need to do is just a commutator, whatever the commutator you get, and you're going to write the following way. So this is how do you do the calculate the commutator. So this is the operator, and then you can. And in the end, I have to tell you what the initial condition look like this. So you will be able to understand how this Heisenberg equation can be used for this. So this is one. Any questions so far? Any questions so far? Anyone of you? Okay. Let's go to the next page, please. So this, essentially, the next page is about the chapter 4. How do we find an eigenfunction of LZ? And that's almost, so basically, you need to remember the operator LZ. So this operator LZ, so this equals like this. So this operator LZ. And something like this. So then you need to remember that's operator. And of course, the remaining ones also similarly. And how do we start LZ first? And then find, why do we start LZ first for L squared? And next question. Toby, got a question for me?
No, my computer just like
went
nuts on me.
Rolled it?
There we go.
Okay. So that's the LZ, how we found that. And the main reason why we start from LZ first for L squared is because they have shared common eigenfunction like this. So what the underlying principle is the two commutators, if they do to operate the commutator, they share the common eigenfunctions. And that is. So some basic parameters for the hydrogen atom in a Bohr model, like Bohr radius and Bohr and ground state energy, these are so basic you need to remember them. And now the commutator about L minus, L plus, and all remaining these ones, you should remember them. And how to do that. At least one of these commutator. For instance, if I ask you to calculate a commutator, and this is what we did already in the homework, like this. Commutator and equals what? So that must be remembered this way. So these are basically commutators. You need to remember that's the hydrogen atom part of it. It's operator. And what's the eigenstate of H atom? And why it has 3 indices like this. So in other words, why we have 3 indices? So psi n, L, n. So why we have 3 indices? Now, I want to explain why we have 3 indices. So suppose inside this we have r, theta, phi, that's the variable. Did you see n here? N equals a main quantum number. This main quantum number, we read the text for last time, but I did not emphasize a lot. The equation, the Schrödinger equation, I'm going to write that down, has L in it. The Schrödinger equation has L in it, but no n. The Schrödinger equation has no n, but it has L in it. But how in the world do you have an n comes out? The reason is that this is due to the boundary condition. This is due to the boundary condition. And this is due to the boundary condition. And numerically, so this is due to the boundary condition. Essentially what we said is that when we do the intervals like this, so we start with them 0, and we will assuming, watch carefully, assuming to the infinite. So suppose this point is called infinite, like this. This is the radius, r, goes to infinite. So when I increase my r, gradually increase such a way to the infinite. Now you see what happens. We will require this wave function we will require this wave function when r at infinite, we require this wave function at a boundary equals 0. So in other words, the reason why we get this n out is due to the boundary condition. The boundary condition is that when psi r goes to 0, or goes to infinite, and psi goes to 0. And this is a constraint. This is a constraint. When you have constraint, then the level are quantized. So energy level are quantized. So therefore, when you have this boundary condition, so then this n is just quantized in this sense. So to be more precise, what we really mean is the following. Because you see this wave function, look like this. This is the eigen equation. Eigen equation, the solution is infinite many. The reason was, if I choose a different E, I will end up with a different psi. Because you have one equation, you have two unknowns in it. That's the basic. One equation, you have two unknowns. How many solutions you could possibly have, Cody? One equation, you have two unknowns. How many possible solutions? One equation of two unknowns, how many solutions we possibly have? Infinite, of course, infinite. Because it's just like x, Cody, look like this. xy equals 2. xy equals 2. You can choose any arbitrary x, you can find a y. Make sense? This is what happens here, exactly the same way. So when you have eigen equations, you have two unknowns, that's why you have infinite number of solutions. In order to denote this infinite number of solutions, we'll use the letter n. Make sense? Because otherwise, you fix this guy, the entire thing is fixed. But now, because you have a boundary condition, you have two unknowns. That's why for the different L will come out. This is analytical constraint. Let me write this analytic constraint. So in other words, analytically, if you look at other books, they will tell you, okay, that's the constraint. Now the numerical ones, which we did last time, constraint. They are exactly the same, of course. There is no difference. So the numerical constraint is because the grid mesh points are finite. Grid mesh points are finite. For instance, suppose let's say start from 0 all the way to let's say to 1 board, so this is 1 board. But now when I discretize these mesh grids, like these mesh grids, well, I have to choose some points somehow, right? I cannot say infinite. Then if I choose more, and this will have a more, in other words, if I choose 20, this will be 20 ends. 100 ends. And then infinite, well, you got infinite points, that's why n goes to infinite. Make sense? So analytically, it's easy to see why it's going to infinite. But numerically, how do you do that? Well, numerically, we discretize the entire things. So then you will see some, I will upload a video to show you how do we calculate wave function for your homework. I already created one. And you will notice that if I plot the wave function, some of these wave functions, for instance, if energy En larger than 0, if energy En larger than 0, which is positive, when you plot a wave function, it's crazy, like this. So this is R. Just to remind you, in our S orbital, it behaves look like this, right? S orbital look like this. And P have a 1 oscillation, whatever. If your N larger than 0, the wave function look like this. Wave function look like this. And this is so-called continuous states. Because oscillate all the time. Remember, the wave propagated all the time. That's where it'll look like. These are called continuous states. Make sense? So continuous states, that's why I like this code, was that you can check any eigenvalue you want. So that's gave you the oscillation in this case. So this is I explained such a way that you guys will be able to see them clearly. And now what I want to show you is the next part of the question. So let me see what the next question is. How do we numerically we discredit? What is a grid mesh? Grid mesh is essentially the separation of these points that we have used. So why does ENL has two indices? So one is directly from the equation. Second is a boundary condition we end up with. You got it? You got it? So that's a boundary condition we end up with. Okay, so that's the conceptual review. And I also upload the sample exams for exam 2 and 3, because my last time when I taught this, we have 2 exams overlap slightly. But if you guys have any questions, just let me know. I looked at the sample exams, probably our second exam similar. Not more difficult, but similar in many ways. Sounds good? Okay, so that's now when you reviewed it, and make sure if you have questions, and I will be, you need to send the question to me, and I will be able to answer it. Any question before we close this? Okay, no question. Okay, so I'm going to end this now. All right. So today we're going to move on a new chapter. I prefer to start a new board. How about that? So that will make things a little more exciting. So let me get back to my first board over here, and I want to explain what we will do for this new chapter. This new chapter has somehow different undertake, so which I'm going to show you now. It's also much more applicable in many ways, so I want to explain one at a time. So this chapter is a method. Now, if you look at the other books, they will wait until very end to talk about the method. And when we were teaching using this book, and we gradually realized it will be a whole lot better, give the students some kind of a wiggle room so have think through it. If you just keep on going, students won't be able to follow easily. So I just somehow just like a pause. So this will be chapter 5, and make sure you do write the notes down, because some of these notes are quite important. And we will talk about approximate methods. In this chapter, the approximate methods is time independent. So it's called time independent method. And you may not like so much something approximate, but approximate method is much more powerful. Approximate method is much more powerful. We can deal with a whole variety of the systems which we want to deal with, and I will show you in this class. In our class, we will cover 2 main methods. The first main method called the perturbation. Perturbation method. So the perturbation method, which means perturbatively make the things a little bit of work better and better. So you can improve upon that. The second method, I hope we have time to do that, called the variational method. They have a different take on that. One is called the perturbation method, and the other is called the variational method. They have a different undertaking involved. And the thing that we won't be able to cover this class, we have so-called a matrix method. And these methods is basically numerical. So this method is numerical. You can solve it numerically in a Gaussian equation. Like a hydrogen code is exactly follow this trend. Essentially, we will use 2 different ways to set up a matrix. One is the one which we already did called grid points, grid mesh. So we use the grid mesh. Essentially, you separate the continuum of the radius or whatever the angle you have and make it discretized. So that's grid mesh. The second is the basis functions. All these, what they're doing is essentially they want to set up a matrix. So you have grid mesh, you can set a matrix, and the basis function also set a matrix. If you want to explain this to anyone who is unfamiliar with these ones, you best basically tell them these are just our coordinates. These are just our coordinates. So the basis function of grid mesh are our coordinates. Just three-dimensional coordinates, you have x, y, z. Here we have more dimensions, we have more coordinates, so to speak. That's why the people call it Hilbert space. Hilbert space. This is the functional space, that's called a Hilbert space. Do not confuse the Cartesian coordinates is because of this reason, but they mean exactly the same. There's absolutely no difference between these two. So this is, I just show you sort of an overview of what will happen. Now, let's go to each one of this a little more detailed. And I will show you a big picture first, and I'll show you key steps, and we'll read the books, and we'll show you how it works. So at least in your mind, you have something you can work with. So this part is going to be straightforward, but it's a little bit sometimes tedious. So now I'm going to show you how we will work out. So our first section, section 1, we will work on so-called the non-degenerate perturbation theory. So it's a long sentence, and it contains a lot of information which you have. So did you see we have keyword called non-degenerate, which means no state have the same energy. So in other words, what we'll deal with is a system there is no degeneracy. So that's involved, and then we will on that. So that means no degenerate. I want to show you the key ideas and limitations. So key ideas and limitations. It's not perfect, but sometimes it does work. So essentially, the key idea is that we're not looking for the entire energy level of a complex system. We're looking for very approximate wave functions for a single level. Find an approximated wave function to a single eigenstate. So now we're looking for just a single state, not entire state. You may think if this is a limitation or advantage, it's up to you. But it's basically what it does. Did you see I have a subscript k here? In other words, this k is the only state matters to me. Only state. This is the only state that matters to me. I'm not interested in the k plus 1 or k minus 1. No, I'm not interested in that. I'm only interested in that particular state k. Did you see I use the psi here? This psi refers to the wave function or eigenstate of the system. And we try to find an approximation to this psi. Psi k, so it's supposed to be psi k like this. And that's that one. Now, part B, Did you see no state has same energy? So this is what we use the mathematics, put the things down. So non-degenerate means the following. Means that the k minus 1 not equals k ek not as equal k plus 1. Like this. So in other words, at least within that particular energy window, we're not the same. Let me schematically show you. Suppose this is your ek. Suppose this is ek1. Suppose this is ek2, or ek plus 1, like this. This is minus 1, minus 1. So the energy level are separate. They're not exactly the same. So that's the condition. This is also the some sense limitation. We cannot deal with these states are degenerate. No, we cannot deal with that. The states must be not degenerated. So that's the mathematical way of saying things like this fashion. So this is what we want you to remember. Now here is a box, folks. You must write this down. This box is quite important, so therefore I'm going to use the blue pen to show you. Otherwise, you totally get confused. When we use letter E to representing that, this means the eigen energy of the system. So this is the eigen energy of the total system. That's the E. So this is the eigen energy. Now I'm going to use the different color to show you my the epsilon. It looks like E, but it's an epsilon. This epsilon is the energy of, watch carefully, an unperturbed system. Now, two keywords shows up. You need to pay close attention. One case that I said here is the perturbed system. The other is a non-perturbed system. So these two are different. So that is quite important. In other words, so this one here is the original entire system. Here is unperturbed system. I'm going to call this is 1 and this 2. Folks, could you write this down? 1 and 2. We have two different systems going on. One is the original system, include everything. The second one is unperturbed system. And my psi, this is the eigenstate of the system. While phi here is the eigenstate of the unperturbed system. So this is again system, unperturbed system. These two are different. They're not the same thing. If you get confused on this, then you won't be able to comprehend what we will do next. So this is of the conceptual difference. You need to be very, very careful, which is we will now explain. So again, we have two differences. One is a 1, one is 2. They're not the same. In order to understand why we need to separate them, and we will explain now, that is where the key step comes out. So this is where the key step comes out. Are we good so far? Any question? Any question going to help you? So just a rotate. Just remind you. These are the original system which we're looking for. We don't know yet, but this epsilon here is the energy which we know. So that is a key idea. So this is my key step starts. Why this pen doesn't work? Key steps. I want to show you the key steps. How do we do the calculation in this way? The first step, split the system. What do you mean by a split system? Well, suppose my original system is represented by H. So this is the original system. This belongs to system 1. In other words, the entire system. It contains two different portions, H0. This means the unperturbed system 2. So this is the system that we're looking for. Now, where is the perturbation? Well, this perturbation comes up. Folks, leave some space here. Leave some space here. And I will insert a constant before that. The last term called H sub I, this usually called a perturbation Hamiltonian. Perturbation Hamiltonian. This is the perturbation Hamiltonian. If you put in the laser field, that's the interaction between system and the laser. If you put an electric field, that would be system with the electric field. Magnetic field, that's system between. So that's what H I. So this I, in my mind, is really called interaction. But of course, you can denote it whatever you want. It's just a small term. Now, the smallness must be guaranteed here. This guy must be somehow much, much smaller than the first term. So essentially what we did was split the system into two. One is the original, the non-interactive term, which is unperturbed, and this is where the perturbation comes out. Okay. Now we also assumed, that we already solved for the problem for the H0 or system 2. In other words, we already know this guy's here. So in other words, the assumption is that based on the prior knowledge. So we assume that if the isolated system or unperturbed system, we already found the eigenvalue and eigenfunctions or eigenstate. So this is assumed. We already found this. But this is unknown for the moment. So that's the assumed. So you must assume that. If you don't know that, you need to solve for that first. So usually, this is the smaller in this case. Now, did you see I have a word called the perturbation? Did you see I have a word called the perturbation? Did you see it? Did you see a word called the perturbation here? The perturbation comes out, we're plugging one factor called the lambda. And this guides us to develop a scheme to find perturbation. This lambda is called a perturbation parameter, or perturbation order. It's called a perturbation order. And why is a perturbation order? You see immediately what will happen. So in other words, let me check the quality of video. Just want to make sure video. Oh, very good, I think. So that is called perturbation order. So what we want, we are going to show you why this is called order. Folks, you see, if my lambda equals 0, then you will see immediately h hat is going to equal h0 hat, right? Exactly the same, because if my lambda equals 0, and this means that this is called zeroth order perturbation. So this is zeroth order perturbation. So I use simply PT, perturbation theory. P means perturbation, T means theory. So this means zeroth potential perturbation. And if lambda equals 1, and then we will have 4 Hamiltonian. 0, 1, I. So this is our original system. So the order lambda allows us to track which order we are on. Either first order, zero order, whatever. So that is order is a goal for us to track that particular order. So this is the one which we have. So this is my the first step. We're going to split the system into two. Once we split system, the second step, expand. We won't call it split. Expand. Aside in terms of orders. So we expand the wave function psi in terms of these orders. First order, zeroth order, first order, and keep on going, second order. And that's where the order, perturbation order, is going to come into play. So this is what we will have, and this is called the perturbation theory starts. So this is in terms of orders, and I'm going to show you similarly. Folks, leave some space here. Leave some space here, because I'm going to show you another equation shortly. Leave some space here. And so now, this psi, it will carry an index. Folks, could you add back index? Our hope is that we are able to expand this guy into the zeroth order, okay, zeroth order. First order, you see I use a lambda now, so this allows me to denote first order. And this is the first order. Second order. And these are one parenthesis here. These are orders. It's not exponent order. Just denote that this is the first order, second or third order. So that is what we are using here. So, and you could have keep on going like this. So this is our wish list. Essentially, we wish that we will get this way. It's not done yet, done deal. And then I want to pause here for a second. For zeroth order, did you see I have a precise 0k? The zeroth order, this must equals 5 sub k. The 5 sub k, forgive me, 5 sub k. Because you see, if the zeroth order, this go back to the original homogeneity, make sense here? So therefore, the eigenstate must be exactly the same, because this will go back to the same perturbation. So this must be exactly the same. So now with the zeroth order, you don't need to calculate, just regularly use them. So this because it's zeroth order. But of course, the other order is different. And this is the psi. And now we can include EK as well. Could you guys write down EK in terms of these orders? So wave function, I expand that, and then my energy is exactly the same. Essentially, I copy everything from the top. Copy everything from top except change psi to E. The remaining term are exactly the same. I just copy everything, EK, like this. So there is no need to do anything except change psi to EK. Psi to EK, and then I have this expression comes out. So remember, what we did was we essentially changed the psi to k. Now, for the zeroth order, this ek 0, it must be equals epsilon k. The same idea, because they have zeroth order, so these two terms must be exactly the same. And that is our second step. Now I want to show you Third step. Step number 3. What we will do, we do the following. We will start with we insert 2 equations. This equation is called equation number 1. This equation number 2. So we insert 1 and 2 into h hat psi k, e k psi k, like this. The last equation, Toby, probably you're looking at, this is just our wish list, which is eigenstate. Did you see with this eigenstate, eigenequation? So this is our wish list. We didn't solve, which is this our wish list. So essentially what you're going to see, we're going to plug in this h over here, psi over here, e over there, and solve it. So that's the key idea. Now, the good news is that this is basically done. And then what we need to add one more sentence and match terms by term according to lambda. So just match term by term according to lambda. So if the lambda is first of all lambda squared, all these coefficients will be same. Lambda first order, lambda itself, all these coefficients will be same. Third order keep on going. So you just match both sides. And so this makes things a whole lot simpler. And this time we're going to show you I want you to read that. Folks, let's go to page 134 and that equation 5.1.5. Starting from this equation. Let's go to page 134. Everybody, page 134. Equation started with 5.1.5. And we're going to read this once here now. 134. Here we go. Okay, waiting R. That'll be good. 134. Are you on which page do you have, Aisha?
74.
74. Okay, good. So the equation is 5.1.5. So that's the equation. Cody, are you on page 134?
Yeah, that's right.
You're right. Okay. Toby, you're already on that page, dear? Okay. So you see, it says the paragraph about 5.51, and we substitute these into that equation. So left-hand side we get this. Toby, could you read that paragraph? We substitute stuff.
We substitute equation 5.1.3 and 5.1.4 into h hat 5k equals e 5k. The left side of the equation must be equal to the right side of the equation. Do you want me to read?
Yes, please read that.
Open quantity h hat naught plus lambda h hat of I closed quantity times the open quantity 5k is the zeroth order plus lambda 5k is the first order plus lambda squared 5k to the second order plus etc. closed quantity equals open quantity equal ek to the zeroth order plus lambda ek to the first order plus lambda squared ek to the second order plus etc. closed quantity open quantity 5k to the zeroth order plus 5 lambda 5k to the first order plus lambda squared 5k squared plus etc. to the closed quantity. Equation 5.1.5 is the mother of perturbation theory and contains all the details. We're going to multiply them out on both sides and compare them term by term according to the lambda.
Well, thank you so much. Cody, could you continue on the next paragraph, please?
We start with equation 5.1.5, focus on the zeroth order terms with lambda 0. Lambda 0 is h naught psi sub k of zeroth order equals ek 0 psi k 0, where the heading lambda 0 reminds us that we are working on zeroth order. Comparing it with equation 5.1.2 reveals that the zeroth order wave function psi k 0 is just the eigenstate times 5k of h and k. Psi k of 0 equals phi k, and ek of 0 is just epsilon k. Ek of 0 equals epsilon k. This makes sense since there is no perturbation, we surely get the eigenstates of H naught.
Great, thank you so much. Aisha, could you read the next paragraph, please?
Next, consider lambda 1 terms. Lambda 1 is h hat naught psi sub k to the first order plus h hat I times psi sub k to the zeroth order equals e sub k to the zeroth order times psi sub k to the first order plus e sub k to the first order times psi sub k to the zeroth order. Plugging psi sub k to the zeroth order equals phi sub k and e sub k equals epsilon k. Into this equation yields h hat naught times psi sub k to the first plus h hat sub I times phi sub k equals epsilon sub k times phi sub k to the first order plus e sub k to the first order times phi sub k. The reader can easily remember how these terms are written by noting that every term consists of two terms, where one term is the zeroth order and the other is the first order in h hat sub I.
Could you finish the last paragraph? Sorry.
To get e sub k to the first order and psi sub k to the first order, we carry out two calculations. A, multiplying equation 5.1 by phi sub k star from the left and then integrating, and B, doing the same as A, but with phi m not equal k. This procedure is standard and works for the second order corrections as well.
Okay, thank all of you very much. It's quite difficult to read it when you have subscript, superscript, and full access. Okay, that's the end of it. Okay, see you guys on Wednesday, and if you guys have any questions, just let me know. Sounds good? Okay, cool. Let me stop recording.